We're going to talk about two more sampling techniques, dither and oversampling. First, dither. Sometimes rounding error is correlated to signals. We heard that with the very low bit rendering of a sine wave where we started to hear harmonics. Correlated just means that our assumption that the rounding error can be represented by just uniform random distribution is no longer true, that somehow the rounding error is related to the signal itself. And what dither does is adds analog noise prior to quantization. It may seem odd to be adding noise to a signal on purpose, but what that does is it decorrelates the rounding from the signal, and so that the rounding error is actually just noise, which a lot of times is more acceptable and less audible. It's typically the noise that you add has a peak-to-peak amplitude of one quantization step, so it's a very low-level noise. So here's an example of what can go wrong. This is a heavily quantized, undithered sinusoid signal. And you can see that what used to be what should be a sinusoid with an amplitude of about 1.5 or 2 quantization levels has turned into this sort of repeating sequence of stair steps and pulses, which will, when it's if you took the Fourier transform of this, it would decompose into the fundamental frequency that we're trying to reproduce, along with a bunch of harmonics. So we know this because it's a non-sinusoidal periodic signal. It must have harmonics. These harmonics could be up in regions of frequency where our ears are very sensitive, and we're also just sensitive to spectrum. And so this kind of distortion or error is really bad. On the other hand, if we add noise before we do the sampling, then and quantization, then we get something much less periodic and much more random looking, and it still doesn't really look like a sinusoid, but in fact we're much more likely to perceive this as a sinusoid plus a very low level of noise. And in practice, because the noise is only at one quantization level or so, the noise should be inaudible. Okay, so here's an example with no dither. Wow, that was sounded horrible because this sine wave was being systematically distorted and clipped by the quantization. Now here we've added dither, and you should hear noise, but it'll sound much more like a sine wave. Now again, these are extreme examples with only a few bits of quantization to make the effects really pronounced. In practice, the noise that you add in dithering should be inaudible or close to it. Now I want to talk about oversampling. Oversampling is a technique that was developed to address the problem of building analog filters to do the pre-filtering and the reconstruction. You may remember from our description of A to D and D to A conversion that filters are involved. These are in the analog domain, and good analog filters are tough to build. The idea of oversampling is you digitally reconstruct the signal at a very high sample rate, and that allows you to build simpler, less expensive analog filters. So here's how this works. Suppose this is the signal represented by our digital samples. So here's the Nyquist frequency right here, and here. So we have a full spectrum signal, and of course, since it's sampled, the spectrum repeats with an offset of the sample rate. So our goal, if we were building an analog filter, well, let's see. Our goal would be to extract just the spectrum up to the Nyquist frequency. Okay. So we have to build a filter that filters the signal kind of like this. After we convert to analog, we've got these pulses, and we run it through a filter that has a very sharp cutoff right at the Nyquist rate. Okay, and achieving this sharp cutoff is the difficult task for analog components. But if we can do it, then we'll have great digital to analog conversion. So let's go back to our signal and think about another way to do things. Suppose that we could resample the signal digitally at double the sampling rate. We've doubled the number of samples, and what those samples represent is this spectrum, okay, which includes all of these alias frequencies, but in the digital signal. We can digitally filter this spectrum, everything below the Nyquist rate, so we're going to filter it to what is now half the Nyquist rate, which was the original signal that we want to recover. And so the digital signal now looks like this. Okay, and notice that we've in the digital signal there are no frequency components up in this region. So now when we convert this to analog, we don't have to build a perfect analog filter. We can build one that starts to roll off somewhere above half the Nyquist rate and reaches zero, or essentially zero, when it reaches the Nyquist rate. Okay, so this very smooth kind of filter is much easier to construct and much less expensive and more accurate, and so on. So the filter removes those frequencies, and we have good digital to analog conversion and no aliases.